Now let us discuss advanced memory instructions. So advanced memory instructions is where we can actually see the power of the x86 instruction set. So what good is a complex instruction set unless it gives us some instructions that make our life really easy? And so there has to be some justification for the C in CISC. So we'll see that with advanced memory instructions. So typically, so let me illustrate a typical case. Typically, some instructions will prove to be useful if we look at certain common programming patterns. So a typical programming pattern is that we move a large amount of data, like a large sequence of bytes, from one memory location to another memory location. So instructions that help us in moving a long sequence of bytes from one memory location A to memory location B, these are known as string instructions. The string instructions make special use of the EDI and ESI registers, as we had discussed in one of the earlier slides. EDI contains the default destination and ESI contains the default source. So the first instruction that we need to introduce in this category is the LEA instruction, because this is what will be used in the subsequent discussion. So this is very important. It's like the bedrock of all string instructions. So LEA means load effective address, and it is used to load an address into any register, in particular the EDI and the ESI registers. Right? So in general, LEA can be used to load an address into any register, but we will mostly be interested in EDI and ESI in the later discussion. But let's look at the generic case first. So the standard format of LEA is this. So the standard format of LEA is register, so it takes two operands. It's a two address format instruction. It takes a register and a memory. So for example, in this case, we have a displacement, we have a scaled index, and we have a base register. So how does this differ from the move instruction? So what this does is, instead of actually loading something from memory, it considers this memory address and simply computes the address part, does not access memory, right? So this is very important. Does not So this is very important. It does not access memory per se, right? By itself, memory is not accessed. What it alternatively does is that it considers the memory operand, gets the address in memory, computes the address, right? Loads. It's called essentially. It should rather be called compute effective address. So it computes the address, does not access memory, and transfers the value of the address, which in this case is this. Right, the address transfers the value of the address to the destination register, which is EBX. Right, it just helps us compute the address. So let's look at our first instruction, which makes our life slightly easy. It's the stosd instruction. It does not have any operands. So what it does is this: it saves the value that is there in EAX to EDI, the memory location in EDI. So basically it treats EAX as sort of as a default source. Essentially it's a store instruction, right? So EAX is the register that has a default source. So it takes the value in EAX, assumes that EDI contains a memory address, accesses memory at that address, and does a store, right? So EDI is assumed to contain by default a memory address, and the value in EAX is stored over there. If the value of the DF flag, so in the flags register is essentially the DF bit. It's not the DF flag, it's the DF bit in the flags register. So maybe I should make it slightly more specific. If the value of the DF bit in the flags register is set to 1, what the stosd instruction subsequently does is that it will subtract 4 from the EDI register, because we are considering a 32-bit instruction set. So it will subtract 4 from the EDI register. If the value in the DF flag is 0, instead of subtracting 4, it will add 4 to EDI register. So think of it as a post-indexed addressing mode, where we do a store to memory, the address being in EDI and the source of the data being in EAX. After doing that, we either increment EDI by 4 or subtract it, or sorry, we either decrement it by 4 or increment it by 4. Why 4? Because 4 means 4 bytes and we are considering a 32-bit instruction set. And whether we subtract 4 or add 4 depends on the value of the DF flag. The LODST, this instruction is a load string instruction. It also does not have any operands. What it does is essentially the reverse of the previous instruction, stosd. It saves the value in ESI. So ESI is considered as the source register. So ESI is considered to have an address, and the address within square brackets becomes a memory address. So it saves the value in memory, whose address is in ESI, to EAX. So this is like loading. You're loading from memory with the address being the contents of ESI, right? The memory location is in ESI. And here also we change the value of ESI. So the value of the DF flag in the flags register is 1. Then we subtract 4 from ESI. Otherwise, if the value in the DF flag in the flags register is 0, we add 4 to ESI. So this is a post-indexed addressing mode, where what we do is that we first access memory, in this case perform a load, right? Perform a load from the memory operand ESI. ESI contains the address, and then we subsequently modify the contents of ESI. We either subtract 4 or add 4 depending upon the value of the DF bit in the flags register. Alright. So let me summarize the memory instructions. So the first instruction that we discussed in this interesting set is LEA. So LEA is load effective address. So it has a simple form where the first and the only source operand is a memory address, is a memory operand, but we do not access memory. We compute the value of the address and store it in the register. Subsequently, we introduced stosd. So stosd is a part of, there are many kinds of instructions can be there. So it's a part of a set of 4 instructions, which are stosb, stosw, d and q. So you already know what these stand for. B stands for byte. So a byte is 8 bits. W stands for a word. So a word is 16 bits. It means that transfer 16 bits. D is, we have been using D, which is a double word, which is essentially 32 bits because our example is in 32 bits. Q is 64 bits. So this will be useful in an instruction set with 64 bits. So depending upon the type of instruction that we are using, we add the right suffix. So since we are looking at a 32-bit instruction set, we use stosd. If it's 64 bits, use stosq. So what does this do? Essentially it reads the value in EAX, saves it in the location, the memory locations stored in EDI. Subsequently, it augments EDI. It sets EDI equals EDI plus 4 times minus 1 to the power df, where df is the flags bit. So if df is 0, this is EDI plus 4. If df is 1, it's EDI minus 4. So LODST is the same thing, same format as STOS. We used LODSD, and because it's a 32-bit ISA, LODSQ could have been used if it's a 64-bit ISA. So here what was done is that this is the reverse of STOSD. Here the source address in memory is stored in ESI. So we read the contents of that, store it in EAX, then we augment ESI. So we can either add 4 to ESI or subtract 4 depending upon the value of the DF bit. If the DF bit is 0, we add 4. Let us now introduce the MOVEST instruction. So this is also part of the same family of instructions. So in this case, what we do is that we read the value, we read a memory operand and we transfer it to another memory location. So MOVEST also works without any operands, without any source or destination operands. Sorry, this should have a square bracket. So what we do is that we read the contents of ESI, and so basically ESI contains the source address. So you go to memory, access the source address, read the contents, and we save it in the memory address pointed to by EDI. So think of it as a load ST and a subsequent store ST fused into one, right? So this is exactly what it does. Subsequently, we augment ESI. So we add 4 to it or subtract 4 depending upon the flag bit. One more mistake. So this DF should be at the top. And similarly, we do the same with EDI. We either add 4 to it or subtract 4 to it depending upon the value of the DF flag bit. We have two more instructions, STD and CLD. The STD sets DF to 1, and CLD, which is like clear D, it sets the direction flag to 0 depending upon what we want to do, whether we want to add 4 or whether we want to subtract 4. Alright, so let us consider an example. So let's see, what is the value of EAX after executing this code snippet, right? So basically this code snippet is fairly complicated. So we need to take a look at each of these instructions and see what is the value of EAX at the end. So let's see. First we have a move instruction. So we move the value 192 to ESP plus 4, and we move 32 bits, so we move a D word, a double word, 32 bits to the location ESP plus 4. So this is the stack pointer. The stack pointer is pointing to a location, to the location on top of that we save 192. Then we load the effective address into ESI, which is ESP plus 4. So let's assume that ESP was 1000. So at this point ESI is equal to 1004, right? So which is this location 1004. Similarly, we load effective address of ESP plus 8. So this is EDI will be equal to 1008, which is actually the address just above it, 1008. Then we execute the MOVEST instruction. So the MOVEST instruction will transfer 4 bytes from the memory address specified in ESI to the memory address specified in EDI. Fine. So what is there in ESI? In ESI points to 1004, which has 192. So these contents will get transferred over here. So 192 will get written over here. Subsequently, if we access ESP plus 8, which is a location 1008, which is there in EDI, and we transfer the contents to EAX, what do we get? We get the same, so these contents get transferred to EAX. So what do we get? We get 192, right? So since we write 192 in the memory address specified in ESI, we shall read back the same value in the last line. So this is a small and simple example. Let's now do something. So where is the power of the string instruction? So what we have seen is, we have seen the LODST, STOST and MOVST kind of instructions, which are essentially shortcuts of load instructions. The MOVST instruction actually fuses a load and a store into one instruction, but that is hardly any power. We are looking for something clearly much more. So let's consider an example and let's see what can be done. So let's assume that we have a 10 element array of integers. The starting address of the source array is in ESI and the starting address of the destination array is in EDI, and essentially we want to copy the source to the destination. So the first thing that we do, which we should always do for such kind of codes, is that we should set the value of df, the data flag, to either 0 or 1 depending upon what we want to do. In our case, we want to count upwards, start at the lowest element and keep going up. Up means towards higher addresses, so we set df equal to 0 by calling the CLD instruction. Then we initialize the loop index of the array, so we set ebx equal to 0 and start a loop. So we call moveST. So what it does is that it transfers the contents of the memory contents from ESI to EDI. So this it does, right? Subsequently, we increment EBX, which is the index. We compare the index with 10. As long as the index has not reached 10, we keep on iterating, right? So basically, if the index is not equal to 10, we do one more iteration. And mind you, since the moveST has a built-in post-increment operation, both EDI and ESI are incremented with 4 bytes. We don't need to explicitly increment or in some other cases decrement EDI and ESI. So they are being incremented automatically. So nothing needs to be done. So we just keep on calling moveST in a loop. That's all that needs to be done to transfer one array from a source location to a destination location. This sounds simple enough in the sense it takes 6 instructions. Otherwise, it would have taken slightly more because we would have had a load and a store. It turns out that this is not the end. We can do something better. So let me introduce the rep prefix. So rep basically means the repeat prefix. So the semantics is that we put rep. So rep is the starting of the instruction and then we specify the instruction. Any instruction we put rep before it. Example would be rep moveST. So what will it do? So it will consider the value in the register ECX and let's say its value is val. It will execute the moveST instruction val times. Right? So basically this is a very powerful instruction because one instruction incorporates a loop inside it. So what will this do again? It will repeat the instruction inst, the same val times, where val is the contents of ECX. So for example, if ECX contains 10, the rep prefix will ensure that the instruction after it gets repeated 10 times, and every time the value of ECX will get decremented till, and at the end it will become equal to 0. So what do we do? Here is a simple piece of code. So we call the CLD instruction first. We set df to 0, which is something we need to do. In this case, we are looking at 10 iterations. So we set ECX to 10, and all that we do is rep move VST. Voila, we are done. It's as simple as that. So let us look at the previous, so let us look at this piece of code, which is 6 instructions. And let us now look at this piece of code, which is only 3 instructions. And the fantastic thing is that we have effectively incorporated an entire loop into one instruction, and we are all done. So transferring a huge amount of data from point A to point B is not a big deal at all. We'll just have to execute 3 instructions in sequence. Let me go through these 3 magic instructions. So we have CLD, which essentially indicates the direction in which we will traverse upwards or downwards in memory. In this case, we decide to go upwards, so we set the DF flag to 0. Subsequently, we set the number of iterations in ECX, which is 10. And then we execute movest 10 times. So movest will, what will it do? It will essentially read the contents of ESI, access the memory location, transfer them to the memory location pointed by EDI. Since DF is 0, ESI will be set to ESI plus 4, EDI will be set to EDI plus 4. Alright. ESI gets set to ESI plus 4 and EDI will get set to EDI plus 4. And we just need to execute it 10 times and we are all done. Alright, so now that we have seen the power of some advanced memory instructions, branch instructions, our understanding of integer instructions is per se more or less complete. So we will not talk about it anymore. So we will now move to floating point instructions. So all the students that I have talked to regarding this issue of floating point instructions in x86 have consistently indicated that floating point instructions are fairly complicated, and this is a part that they would rather not study, and they want to focus on something else. But that's not the case. So x86 floating point instructions are not complicated at all, as long as you understand the basic philosophy behind them. So the machine model is like this, that we have memory. So we can directly load constants into memory via the, okay, let me write it. So we can directly store constants into memory. We can directly store constants into registers. Registers can then be stored into memory, and memory values can also be stored into registers. However, floating point registers are sort of, their connections are weak. Floating point registers can only talk to memory, and so loading constants and so on into them is slightly difficult. We shall see how. But their primary interface is via memory. So there is no direct connection between integer and floating point registers. That's point number 1. FP stands for floating point. They can only communicate via memory. And there's also no way to load floating point immediates directly. So that also needs to be done via memory. So once this basic diagram, basic diagram is understood, we are in good shape. Alright, so let's understand what are some of the basic floating point instructions. How are they to be invoked and what is to be done to learn them correctly. So basically one major problem that happens while writing floating point programs is that if students don't understand the machine model, they can make mistakes, and this is something we want to avoid. So let's consider the FLD instruction. FLD is very simple, floating point load. So this instruction pushes the value of the first operand, which can either be a register or memory. So that's the reason actually I've written it twice. I've written a register form and a memory form onto the floating point stack. So let's see. So recall that in the floating point stack, you actually have 8 floating point registers, right? So this is like the FP stacks. I'm not drawing 8 boxes, but that should be the connotation. So the top of the stack is always ST0. So a floating point register is actually a pointer to the floating point stack. And the bottom of the stack is ST7. Right? That is the idea. So essentially the values of registers will change. So if I, let's say, push something onto the stack, let's say push 3.5. So previously there was 4.5 over here, and then I push 3.5. So 4.5 goes over here, it becomes ST1, and 3.5 becomes the new ST0. So when I call something like FLD mem, so the first thing I need to do is I need to specify how many bytes am I interested in. So here this is the memory operand stored, the address stored in EAX. If I'm interested in 4 bytes, I specify the D word modifier. So it pushes a floating point number. Well, it's an FP number, fine. Grammatically, it's still okay. So it pushes an FP floating point number stored in EAX, right, in square brackets, to the floating point stack. So there, if the number stored is 3.5, it gets stored on the floating point stack. Similarly, there is a register form as well, but mind you, this is not an integer register. This register form of the instruction, this is a floating point register. So what we can do is we can do FLD ST1. The floating point registers are ST0 to ST7. So it'll push the contents of ST1 to the top of the stack. So it'll read the contents of ST1. So let's say you push 4.5, right? Because 4.5 is ST1. So then this will again get pushed to the top of the stack, right? So these are the two most common variants of the FLD instruction that we can either read directly from memory, or we can read another floating point register, but we read the contents and simply push them on the floating point stack. Similarly, we have the FILD instruction, which basically what this does is that I stands for integer. So this pushes an integer stored in memory to the floating point stack. So essentially it converts. It does an int to float conversion. Think of it that way. So in this case, we read the value of EAX, which is an address in memory, and we read in 32 bits. But the 32 bits are not in the floating point format, they are in the integer format. So this integer which is stored in EAX is first converted to a 32-bit floating point number, and then pushed to the floating point stack. So what are the basic instructions? FLD, floating point load, and FILD, where actually we load an integer but we convert it to the floating point format and we push it onto the stack. So this is how we load memory values, right? So there are two ways to load a floating point immediate. The first is that we first load its hex representation to memory. And so what do? Let's take a number 3.5. So we'll first, well, this technically should not be load. It's better to call it store, right? It's a better idea to actually call it store. So what we can do is that we can store its hex representation, right? The representation in IEEE, I should also maybe call it the IEEE 754 format. Right, we can store it to memory and use the FLD instruction to bring the value into a floating point register. Otherwise, we can use an assembler directive to store the immediate as a constant before the program starts. So what would the assembler do? The assembler will essentially insert code to basically convert it into hex and store it in a certain area of memory. And then we can use the FLD instruction to transfer the value to the FP stack. So in a sense, both these instructions, both of these points are the same. The points basically say that either the assembly programmer manually converts a floating point number to its hex representation and stores it to memory and then reads it to the floating point stack. The other is we let the assembler do exactly the same thing. So in NASM, we can have it, there is a data section in which all of these constants can be declared, section.data. So what we do is that we can define a 32-bit floating point constant called num, which is, so this specifies its 32 bits, and this is its value, 2.392. So this is something that can be done, that we can specify a number in its decimal format. And so the label here is actually the name of the variable, the memory variable, which can be referenced later. And this is the value. So what the assembler would do is it will take 2.392, convert it to its hex representation, store it somewhere in memory, right, and associate that memory address, right, mem address, with the label num. So that's exactly what will happen. Assembler will associate the label num with the memory address that saves 2.392. In the assembly program, all that we need to write in the case of NASM, but all similar other assemblers have a similar format as well, is that we'll write FLD, D word for 32 bits, and num. So the assumption here is that num will get replaced by the actual value of the memory address by the assembler. So with this method, we do not have to save the hex or binary representation of a floating point number. This will automatically be taken care of by the assembler for us. Alright. So now we will look at another instruction which works exclusively on floating point registers. It is called floating point exchange, or FXCH, right? F for floating point, XCH for exchange. So we can call it FXCH. So here, so it has two variants, and in both the variants, it exchanges the contents of two floating point registers. And ST0, which is the floating point stack top, is always one of the FP registers. If I write FXCH ST3, it will exchange the contents of ST0 and ST3. If I just write FXCH without any arguments, it will exchange the contents of ST0 and ST1. So pretty much, if this is the floating point stack and the top is referred as ST0 and the second is ST1, then essentially their contents will be interchanged. So now that we have taken a look at load instructions, let's take a look at floating point store instructions. So similar to an FLD, we have an FST. It does exactly the same thing. So let's take a look at the two variants of FST that we have. So the FST mem instruction takes a memory address, a memory operand as its argument, and so it can save it in multiple formats, but let's only stick to the 32-bit format right now, D word. So since we are not specifying which floating point register, ST0 is assumed to be king, the stack top. So it takes the contents of the stack top and saves it at the memory address specified in EAX. Alternatively, it is possible to specify a certain floating point register. In this case, what happens is that the contents of ST0 are, so this acts like a floating point register move pretty much. So it takes the contents of ST0 and saves it in this case in ST4, right? So basically ST0 is always the source. We can either save it in memory, we can either save its contents in memory, or we can save its contents in another floating point register. So let us now look at this variant over here, FSTP, which is exactly the same as FST, but in addition, P stands for pop. So let me maybe write here the P over here stands for pop. So it does exactly the same thing as FST, but the additional P, after doing what FST would have done, it pops the floating point stack. So FIST is an analog of FILD. So what this does is that, see here also we specify a memory address and of course the size, how many bits need to be saved. So what this does is that, let's just compare FST mem and FIST mem. So it is this line over here and this line over here. So what this instruction does is that it first converts the floating point number into an integer representation pretty much by truncating everything after the decimal point. That's what it does, that it first converts it into an integer. After converting it to an integer, what does it do? What it does is that it saves it in memory. And the FISTP instruction is the same, that we read in the value of the floating point register ST0. So ST0 is almost always the default source or the default destination. And so ST0 sort of has a special place. It's the top of the floating point stack. And if an argument is not specified, most likely it is ST0. So in this case, in FISTP mem, an argument is not specified which register. So that is ST0. So we convert it to an integer and save it in memory. And because the P suffix is there, we pop the floating point stack. So what have we looked at? So till now we have looked at FLD and its variants like FILD. We have looked at floating point exchange, which exchanges the contents of two registers. We have looked at FST, which stores the value of a floating point register either in memory or in another floating point register. And again, different variants with a P suffix pops the stack, and FIST for integer conversion, and so on. So the main instructions are FLD and FST that we need to bother about, right? FLD and FST. Let us now consider an example. So a 32-bit floating point number is loaded in ST0. So it is present in ST0. Let us convert it to an integer and let's save its value in EAX. So to do this, so one thing that is clear is that from the set of floating point registers, so the direction of data flow is from the floating point registers to memory. So this is a store. So we need to use some variant of the FST instruction. And since conversion to an integer is also there, the instruction that we need to use is FIST, right? FST for store and I for the conversion to integer. So we want to save this in a memory location first, and then transfer it from memory to a register, to an integer register, because we cannot directly transfer a floating point value to an integer register. So what we do is that we assume that, let's say, this location on the stack, ESP plus 4, is available, is free. So there we transfer a D word, or 32 bits, because it's a 32-bit floating point number. The contents of ST0 get written to this memory location. This is what the first statement achieves. Then the second statement is a simple register move, which we have seen in great detail in the previous sections. See, here what we do is that we specify a memory address, and from this memory address we essentially read in 4 bytes into the register EAX. So let us now look at the floating point add instruction, which is in a sense similar to some of the earlier instructions that we have seen. And but let's take a look. It also has different forms, and some of these forms are slightly involved. So let's start taking a look at least the most basic form. So the one operand form of the FAD instruction takes a memory operand as the single source. So for example, FAD dword EAX. So in this case, the contents of the register EAX are taken, memory is accessed, and from there we read in a D word or a double word which is 32 bits. So the assumption is that a floating point number is present over there, and we take it and we add its contents to st0 and save the results in st0 as well. So st0 can be thought of as the default floating point register for this instruction. The other form is where the instruction takes two registers, two floating point registers to be specific, as the operands, and this the form is exactly similar to the add instruction, uh, to the integer add instruction. The only caveat here is that one of the registers has to be st0. So most versions of x86 of the x86 ISA actually require this, that one of the registers has to be st0. So in this case, the add instruction is similar to the integer add instruction, where we set st0 is equal to st0 plus st1. I mean, this instead of st1, this can be st5, it's still fine. So we can say st0 is st0 plus st5. So it doesn't matter. Then the add instruction also has a mode where we can pop the stack. So we use the p suffix. P is for pop. So here what we do, before I explain this, we need to consider one thing, that we cannot store the result in st0 because st0 is going to get popped. So the typical form in this case is that we have some floating point register which is not st0, typically st1, but can be others also. And then we store the result in st1. And so in this case also, it is typically the case that st0 is one of the operands. So we add, so in this case, we so we can think of this as sti, where it can be any st, and any st where I is not equal to 0. Since this is st1, the explanation is that the way this instruction will work, we will compute st0 plus st1 and save the result in st1. That is important because we can't save it in st0, it's going to get popped. Subsequently, we pop the floating point stack. So this means that whatever are the contents of st1 become the contents of st0 after the pop. This instruction also has a mode where we can read in an integer from memory, convert it to floating point, and do an addition. For example, if I have the fi, if I have this I, the character I after f, so the instruction will become fi add. And an example of this instruction would be fi add d word eax. And so here this contains the memory address. So the computation that is being done is that to st0 we add the contents of the memory address. So that's assumed to be an integer, so we convert it to a floating point. We add it to the contents of st0 and save the results in st0. So since all our code has been specific to the NASM assembler, the NASM assembler also provides one more variant of the FAD instruction. So this variant has also been discussed in the book and is there in several examples as well. But this is not a part of the general x86 specification, even though a lot of assemblers do implement it because it's very convenient. But users should keep in mind that the table on top, these are like generic formats which you'll find in Intel manuals. But this is NASM specific. So can be used if NASM is being used as the assembler, and if there are other assemblers that support this particular format, this can be used. There's nothing wrong in it. So this format is a one address format instruction, where the only operand that FAD takes is a floating point register. So for example, FAD st1. So here the default source, the default second source is st0, and the default destination is st0. So we could have very well written f add st4. So the effect that this would have had is st0 is st0 plus st4. So this is very convenient while writing assembly programs, but as I said, this is not a general format of the FAD instruction. So it is possible that in some assemblers this might not work. And so this possibility is always there that in some assemblers it might not accept this format. But wherever this format is being accepted, it can be used. See here, what needs to be remembered is that the second source operand is st0 and the destination is also st0. So similar to add, we have subtract, multiplication and division instructions which work in exactly the same way and have the same variance also. So let me write it down. So exactly the variants that we have seen over here, say they can take a single memory operand as uh, the arguments of the instruction, or they can take two floating point registers. They also have the additional p mode where we pop the floating point stack, and also similar to fi add, you can have an fi sub where we read in an integer from memory, convert it to floating point and use it in a subtraction. So here I'm just showing examples with a default memory operand. So in this case, if this is the memory operand, what we will do is that we will read in the value and subtract it from st0 or multiply it to st0 or divide it to st0, whatever the case may be, and the rest of the variants are the same. So at the cost of uh, so basically to avoid repeating, I'm not talking about all of the variants once again, but essentially to look at what variants are supported, let's go back to this table which shows the variants for the FAD instruction and reuse the same variants for the other instructions f sub, f mul and fdiv. So let's show an example. Let us compute the arithmetic mean of two integers stored in EAX and EBX. Let's save the result. So here there is a catch. So we don't want to save a 32-bit floating point. We want to save a 64-bit floating point. A 64-bit floating point number is a double precision number. So we want to save this in the address ESP plus 4. Let's assume that the memory address 2 contains the constant 2. So basically loading values into floating point registers is complicated, loading constants particularly. So they need to be saved in some memory location, and that memory location needs to be the contents of that memory location need to be transferred to the floating point stack. So let's do one thing. Let's first start by loading the inputs to the floating point stack. So since EAX and EBX contain the two integers, uh, we need to transfer them to memory first because direct communication between integer and floating point registers is not there. So let's transfer them to memory. So let's assume that these two memory locations at ESP and ESP plus 4 are free. Subsequently, let's load them onto the floating point stack. We'll use the FILD instruction, the I basically meaning that a conversion will happen from integers to floating points. So this is what the I means over here. So then we will convert them and we'll load them onto the stack. So basically this value will be at the stack top st0 and this will be at the second from the stack top st1. Alright, let's go ahead. Let's compute the sum of st0 and st1, and so the result will get saved in st0. And let us divide the contents of st0 by whatever is stored in the memory location 2. So what is stored there? What is stored there is 2.0. So let us divide it, and the final result is there in st0. So basically, let's consider an example. If EAX contained 8 and EBX contained 9, So the arithmetic of 8 and 9 is 8.5. So 8.5 is stored in ST0. What needs to be done next? Well, what needs to be done next is that we need to save the result to ESP plus 4 to this memory address ESP plus 4. And we want to save a 64-bit result. So that is the catch. To save a 64-bit result, I'm using the FST instruction. And to just clean up the stack, I'm using FSTP, but it's technically not required. So FST would have been just fine. And then the important point to note is that the Q word identifier is being used. The Q word identifier basically means quad word or 64 bits. So we are saving the result as a 64-bit quantity. And this is being stored at the memory location ESP plus 4. So this is all that we need to write this program. So the program contains 7 assembly instructions, which is not much. Given the fact that a lot is being achieved, we are taking integers, converting them to floating point, putting them on the floating point stack, computing their arithmetic mean and writing them back. So it's a fair amount of work that is being done. And but it's important to understand that what is being used, the FILD instruction is being used to achieve the conversion from integer to floating point. That is point number 1. Second, we are doing a division and a constant 2 is saved at a certain memory address called TWO. And then we are saving the result back, which is a 64-bit quantity using the Q word identifier to ESP plus 4. Now let's take a look at instructions for some special functions. So basically, what is the advantage of having a CISC instruction set? Unless these special functions are supported. So there are many more special functions which listeners can find, readers can find in Intel's manual. But some of the ones that are most commonly used are fabs for an absolute value, square root that computes the square root of ST0 and saves it in ST0. Then cos and sine. One second. Yeah, then cos and sine. So where again the cos of ST0 is computed and saved in ST0 and same for sine. There are many functions, other functions for other transcendentals and logarithms and so on. So the listener, the reader, the user, right? All these three are interchangeable terms. Can take a look at the Intel's manual to find out what are the other instructions that are supported. Alright, so let's do one thing. Let's now compute the geometric mean of two integers stored in EAX and EBX, and let's save the result again in 64 bits at the location ESP plus 4. So the only change that is being done is that from arithmetic mean we have gone to geometric mean, that's all. So most of the code will remain the same, and it genuinely does. So this part remains exactly the same, where we read in the floating point numbers from these two registers. So these two registers contain integers. They are converted to floating point numbers and stored on the floating point stack. Subsequently, instead of an F add, we multiply them. So ST0 contains the product of ST0 and ST1. We compute the square root. So basically ST0 contains the square root of ST0. Right, and then the last line is exactly the same, where we again store it. We use the Q word identifier to ensure that the result is 64 bits, and we store it at the memory address ESP plus 4. Alright, so now let's take a look at comparing floating point numbers. That's important because that's a lot of code that has branches and so on depends on the results of comparison. So compare also has two variants, two simple variants. The first variant is f comma I. So here we compare two registers, let's say ST0 and ST1. So we compare ST0 and ST1. and we set the flags register uh, appropriately. So here the caveat in most variants of the x86 instruction set is that the first register has to be ST0. So that is typically the caveat that is placed. So another variant of the f comma I, the compare instruction. So this compare instruction is very similar to the CMP instruction for integers. So essentially we compare registers and we set the flags. That's a simple basic idea. So we can additionally have the p suffix where we compare two registers and we set the flags register, and additionally at the end we pop the floating point stack. So let's say we don't need a value, we don't need st0 for example. We can do the comparison and then at the end of the instruction we can also pop the floating point stack. So here is a very important point. A lot of students make mistakes in this point, and this is a very common source of bugs while writing assembly programs with floating point operands. So the source of bug is the source of the bugs is as follows. So let me draw a circle over here. The important point is that the flags are set for unsigned comparison, not for signed comparison. So recall that we had different kinds of flags. So basically the condition codes that we need to use are essentially below and above. So these are the condition codes for unsigned comparison, not greater than, less than, or anything else, right? So not definitely not greater than and less than and greater than equals and so on, not these ones. We need to use the condition codes basically B for below, A for above, NB for not below, and so on. So these are the condition codes that need to be used, and these are the condition codes for unsigned comparison. And this is definitely what it is that needs to be used. So this is a very common source of mistakes, because typically students would use the condition codes for signed comparison and they get the wrong answer. So this needs to be kept in mind, that the condition codes that need to be used are the ones for unsigned comparisons. Essentially we need branch instructions of the form JB or JA. Alright, so now let's take a look at a difficult example. It's not that difficult, but it pretty much uses all the concepts that we have learnt up till now. So let us compare sine 2 theta and 2 sine theta cos theta. So those who still remember trigonometry will quickly guess that both of these expressions are the same. So sine 2 theta and 2 sine theta cos theta are the same expressions. Let us verify that they have the same value for any given value of theta, and assume that theta is stored in the data section of the assembly file at the label theta, right, at the memory address theta. And the threshold, so here is the important thing. Let me stop here, right? So how do you compare two floating point variables, let's say f1 and f2? So the nature of real numbers or floating point numbers is inexact, right? So this we have discussed in chapter 2, that comparing floating point numbers makes little sense, basically because the representation is not exact. So essentially, we have a basic question here, that let's say a number of the form 3.0 and 3.0 plus, are they equal or not equal? So this is a broad philosophical issue. So theoretically speaking, they are not equal, but practically they might be equal, and the reason being that we might not have enough bits to specify 3 plus 10 to the power minus 30, right? So we might not have that precision that is required to specify f2, and as a result the hardware might compute f1 to be equal to f2, right? This is theoretically not correct, but real number arithmetic is always inexact. So the best way and the standard method, the standard approach of comparing floating point numbers is like this, that we take two numbers f1 and f2, we subtract them, take their absolute value, and see if this is less than a predefined threshold, like epsilon. The threshold can be arbitrarily small, it depends upon what our tolerance is. So maybe like 10 to the power minus 5 or 10 to the power minus 10. It all depends on what f1 and f2 are. But the main idea is that the way we find out equality is basically by using the fact that the difference, the absolute value of the difference, has to be less than a given threshold. So in this case, let us assume that this threshold is saved at the label threshold. And finally, after the comparison, let's save the result in EAX, 1 if there is equality and 0 if there is lack of equality. So we expect 1 as an answer all the time. So let's now gradually, let's break this example, because the example is kind of long and complicated. As you see, it's a 2-page example. So let's nevertheless try to understand it slowly, gradually. So let's do one thing. Let's first compute sine 2 theta and let's save it in memory, right? So the first thing that we do is that we load the constant theta from memory. So what we do is that we assume that the constant theta, in any value of the angle theta, is stored in the memory uh, label theta. So we load the contents onto the stack top, which is st0, and then we add st0 with st0, essentially compute 2 theta. Then we compute the sine of this. So this basically at this point st0 is equal to sine of 2 theta. Subsequently, we save sine 2 theta into the memory location pointed to by ESP, where we assume that that particular memory location is available and can be used. So since all our quantities are 32 bits, we use the D word identifier. And in addition, we actually use the FSTP instruction. So basically, we don't need the value anymore, so we pop the stack also, right? In addition, so this is in general a good idea, that when we don't need the value, we can additionally pop the stack such that the floating point stack remains fairly clean. Alright, so now let us compute 2 sine theta times cos theta. So let's do the same thing. Let's load theta into st0. Let's create one more copy of theta in st1 by the FST instructions. FST st1 basically sets st1 equal to st0, which is equal to theta, right? So both at this point, at this particular point, st0 and st1, both of them contain theta. Now let's issue the fsine instruction. So the fsine instruction computes st0 is equal to sine theta. Let's exchange. So f exchange exchanges swaps st0 and st1. So at this particular point, after this instruction, st1 will contain the previous contents of st0, which is sine theta, and st0 will contain the old contents of st1, which is just theta. Then let's issue fcos. So fcos will compute st0 as cos theta. Then let's multiply st0 and st1. So st0 will then contain sine theta times cos theta, right? And then let's add st0 with st0. So then st0 will be 2 times st0, which is 2 sine theta cos theta. Alright. Okay. So where are we at the end of this page? We have saved sine 2 theta at the memory location ESP, right? Point whose address is in ESP, and we have 2 sine theta cos theta in st0. Alright, now that we have this, let's do one thing. Let us again load the value that was stored in ESP, which was 2 sine theta, which is sine of 2 theta. So let's load this value into the stack top. So the previous stack top goes into st1. So at this particular point, st0 contains sine of 2 theta, and st1, which used to be st0 before we actually did a push operation on the stack. So recall that any FLD instruction, any float instruction pushes the value on the stack. So st0 becomes st1, st4 becomes st5, st6 becomes st7, and so on. So st1 will be the previous contents of st0, which is 2 sine theta cos theta. Right? So at this point, let us subtract them. So let us subtract this value and this value. And the difference between these two values will be saved in st0. And let us also then compute using the fabs instruction its absolute value. Alright, so what does st0 at this particular, maybe let me draw a line here. What does st0 contain? st0 contains the absolute value of the difference between sine of 2 theta and 2 sine theta cos theta. Alright, so now let's do one thing. Let us read in the value of the threshold, which is the value epsilon, the maximum possible deviation between two quantities that are deemed to be equal. So let us read its value. So when we load its value, it will get loaded to st0, right? So st0 will contain epsilon, and the new st1 will actually contain the previous contents of st0 because we just push the stack, which is this difference over here. So let us compare st0, which is epsilon, and st1, which is the difference, right? Let's just compare. So ideally, what is it that we want? We want epsilon to be greater than the difference, right? The threshold to be greater than the difference. So which means that the threshold is above the difference because it's an unsigned comparison. That's an important point to note, that we'll only use above and below. So we use the branch operation JA, the conditional branch JA, where J is for jump and A is for above. So if JA is true, we jump to dot equal. And at this particular point, since we have found out equality, that the difference is less than the threshold, we set 1 to EAX and we exit. Otherwise, just if this is not the case, we'll set 0 to EAX and then we will exit. But the important point is this should not happen because the trigonometric equality, that is a trigonometric identity, this should hold all the time, unless you know there is some bug in the code. So thankfully there is no bug, and you can copy paste the code as is written onto an ASM window and test. So it should work just fine. And so this is where, and all the time the output should be equal to 1, which means that equality between sine 2 theta and 2 sine theta cos theta exists. So one thing that we get to understand over here is that writing a program with regular x86 floating point instructions is certainly not difficult at all. We just need to understand the nature of the floating point stack. So let me just write down what are the concepts that we need to understand. We need to understand the nature of the floating point stack. That's the first thing that we need to do. So we need to understand that when a new value is pushed into the stack, the rest of the values go down by one position. That's point number one. We need to understand the nature of the floating point instructions, right? So basically, the fact that they treat st0 in a special way and how they work. Then we need to understand the nature of floating point conditionals, that always the above and the below flags are to be used. Right below condition codes are to be used. And the rest is straightforward. The rest is pretty easy, so that's not difficult at all. And we can write fairly efficient floating point code with this. So let me now add an afterword now that we have seen this. Actually, let me add the afterword after the next slide, because that's when I'll introduce two more instructions. So these instructions are typically used as cleanup operations, so for the stack cleanup. So the f-free instruction, which takes a floating point register as an argument, like f-free st4, essentially frees the content of st4 and marks it as clean. So typically it is good programming practice that at the end of a program or at the end of certain points in the program, clean up the floating point stack. Because the floating point stack is a part of the program state. So let's say that another program wants to execute and the current program needs to be suspended. It is necessary to save the complete state of the floating point stack and then restore it. So that is the reason that it is advisable that if floating point code is not used, then we can keep the stack of the floating point clean. So the instruction that helps us clean the floating point stack is finit. So what does finit do? It resets the status of the floating point unit, including the stack and registers, which basically means that it cleans up all the registers if there is, and it essentially says that the floating point stack is empty, right? And it resets the flags and condition codes of all the floating point. I'm sorry, I shouldn't use the word flags and condition codes, but it resets the status of all the floating point hardware, which includes adders and multipliers and all of that, and also similar kinds of hardware. It marks the floating point registers and the stack is empty. So it pretty much cleans it up. Now let me add my afterword. So my afterword is that this is the basic floating point support that x86 processors have. So x86 processors are primarily, 16-bit types, which are the 8086 types. So these are not used very frequently these days. Maybe in some embedded applications, but otherwise not very frequently. 32-bit is still around also in the embedded domain. It's gradually going away, but 32-bit is definitely around. And so this is what is referred as x86 or x86 32-bit or sometimes i386. Then we have 64-bit. 64-bit is definitely around and will be around for a long time. So this is called x86 64. So these are all the variants and versions of the x86 instruction set. The 8-bit instruction set is also there, but that's too old. So the floating point stack has been there since pretty much 1987, to the best of my knowledge, at least with a 387 co-processor whose job was to do floating point operations. So it's been there for a long time. Uh, so this is a basic, and the architecture is somewhat slightly old and primitive. So maybe as an addendum to this book at a later point of time, I'll add the more recent architecture. So subsequently, Intel has introduced many more floating point register sets actually. One of them is MMX. The other are the SSE registers, right? Then recently the AVX registers. So it is possible to use particularly, say, MMX defines the XMM registers, right? There are XMM registers, YMM registers, and so on. But with the XMM registers, a lot of this code can actually get far more simplified. So we are not covering them in at least this version of the book. But my advice to readers would be that if they want to know more, they can definitely read more about these extensions of the x86 architecture set. ISA.